scenario, a softball pitcher's throwing motion can be seen following a circular motion. Question: what are the forces that are contributing to the pitcher's throwing motion? The centripetal force is making up the force tension and the force of gravity. So there are two forces here that are contributing to the pitcher's motion. And the fact that it goes in a circle, those two forces make up the centripetal force that is causing the object to go in a circular motion. Next question: at what point in that circular path will she feel the most tension in her arm? Essentially, solve for the force tension. Taking the positive direction to be towards the center of the circle, at the bottom of the loop, the force of gravity subtracts from the force tension, and at the top of the loop, the force of gravity adds to it. So notice, pointing down is force gravity, pointing up towards the center is force tension. The force tension is bigger because that is what keeps it in its circular motion. On top, force gravity is pulling down and force tension is pulling it down. Notice on the top, both forces are contributing to the centripetal force. Here's the equation. The summation, which makes up the centripetal force, or the centripetal force, is force tension minus force gravity, which is at the bottom. Substitute the values in. Then you have to substitute centripetal acceleration as v squared over r. Then you have to add mg to the other side. Notice here, force tension is equal to mv squared over r plus mg. This is the reason why her tension feels a lot, because that mg is added to the centripetal force. Next, at what point in her circular path will the ball have the greatest tangential velocity? That tangential velocity is essentially asking us to solve for v. So, at the top of the loop, notice that the force of gravity adds to the centripetal force. So here it's Ft plus Fg, because again I am taking the positive direction to be towards the center of the circle. Substitute the values in like before, but this time I divide by m and multiply by r to both sides, so I can now get v alone. Notice here it is Ft plus mg, so that mg that comes from the force of gravity is actually helping the pitcher's greatest tangential velocity. Notice that you're like, wait, I thought the tangential velocity is constant in a circular path. Well, that is true when it is an object orbiting another orbit, when it's just the force of gravity that is supplying the centripetal force. But here, when there are two forces acting on it, you have to make sure, depending on its direction, if it's adding to the centripetal force or subtracting from the centripetal force.